How do dendritic spines change the brain? Imagine tiny branches on a tree that grow, shrink, and sometimes disappear as the tree learns to adapt. That's similar to what happens with dendritic spines in the brain. These small, bulb-shaped structures are found on the branches of neurons, where most of the brain's communication signals happen. They are the sites where neurons connect and send messages to each other. During early childhood, the brain is like a busy construction site, building and shaping these connections rapidly. When a baby is born, their brain has many thin, flexible projections called dendritic filopodia. These filopodia are like tiny tentacles reaching out to find other neurons. Over time, these filopodia develop into mature dendritic spines, which have a head and a neck. The spine head is where the synapse, or connection point, forms. As the brain grows, these spines change in number and shape, depending on what the child experiences and learns. In the first few years, the number of dendritic spines increases quickly, peaking around ages 2 to 8. This rapid growth supports the brain's ability to learn new skills, understand language, and develop motor abilities. During this time, the brain is very plastic, meaning it can easily change and adapt based on experiences. As children grow into teenagers, some of these spines are pruned or removed to make the brain's wiring more efficient. This pruning helps the brain focus on the most important connections and discard weaker ones. Every time a child learns something new or practices a skill, new dendritic spines can form. At the same time, others may be eliminated. This process of forming and removing spines is called synaptogenesis. It is how the brain rewires itself, making new pathways or strengthening existing ones. This flexibility is what allows us to learn, remember, and adapt to new situations. If dendritic spines do not develop properly or are not maintained well, it can lead to problems. Some neurodevelopmental disorders, like autism or Fragile X syndrome, are linked to abnormal spine growth. Too many immature spines or too few mature spines can interfere with how neurons communicate, affecting learning and behavior. In early childhood, the growth and change of dendritic spines lay the foundation for all future learning. Providing children with rich, stimulating environments encourages healthy spine development. This, in turn, supports their overall brain growth and ability to develop new skills. So, in simple terms, dendritic spines change the brain by forming, maturing, and sometimes disappearing in response to experiences. These tiny structures create the physical framework that makes learning, memory, and brain flexibility possible during those critical early years.